nanohub.org.
Online simulation and more for nanotechnology.
So today we are going to talk about a new topic, measurement system analysis. We have seen this slide in the beginning of this class. If we have a production process, we can use many tools to monitor our process and improve our process by reducing production variability. So that's our goal, right? So we have many different techniques, acceptance sampling, design, accept sampling for the products, and process monitoring. For monitoring, we can either use control charts, like we have already learned, or the different types of control charts, or we can use some advanced monitoring methods, like multivariate control charts, or machine learning methods, or we can estimate process capability using the data we collected. But you can see that in all the tasks, data is very important, right? If you have a production, you have a production line, you produce many products. For each of them, let's say this is my product. For each of them, you are always interested in knowing whether it's good or bad. So that's the one decision to make. Is that right? In order to do that, how can we make that decision? How can we know whether a product is good or bad? If I have a pointer, I want to know whether it is conforming or non-conforming to standards. What do I do? Testing. I do many testing, right? But in testing, in this test, you need some quantitative measures to know whether it reaches or not reaches some limit. So that's why we have the concept of classification limits. Is that right? So in order to do this, what else do we need? Let's say we want to measure this response time, this pointer response time. We need a timer, of course. Is that right? If we want to measure the dimension of the pointer, we need some rulers. So all of these are dependent on your measurement systems. Okay, let's say we have specification limits and I have a number of measurements. And then, in order to have one conforming product, do I have to have all dimensions or all standards to be met? Not necessary, because sometimes we allow a certain number of defects. Say you have a TV or a monitor, it's allowed to have 1 or 2 pixels not working. That's okay. It's still conforming. So, but in that case, you need to count the number of defects in a product. Okay. If we want to monitor this, which control chart can we use? The number of non-conformities or the number of defects. Which control chart we can use? We just learned this in last lecture. Is P chart okay? Or X bar chart? And it's what? C or U chart? Which one is the best in this case? Okay. Then we want to review that. Okay. Even though I don't require you to do calculations, you still need to know the concept. Okay, so that's that. Okay, so what if I want to monitor the number of defective products in a batch? Or a fraction non-conforming. We can also use effective rate for this terminology. Okay, if you want to monitor this, which control chart should we use? Non-conforming fraction. What's that? Did you say something?
No.
Okay. So which control chart can you use for this monitoring? It should be P or NP chart. Okay? So this is P or NP chart. This is C or U chart. Okay. So all of these are attributes, right? There's another category of variables we want to monitor, which is continuous variable. And we call that as, what, do we have a name for that type of variables? For continuous variables? Let's say we have quality characteristics. There are two types. One is continuous variable, the other one is discrete variable. Okay. For the continuous variable, what kind of variable can you use to monitor? So this normally can be dimensions or some weight or response time. All of this should have a unit. So for these type of variables, we can use x bar chart, r chart, x bar, s chart, x bar, s square chart, or xi volume range chart. We need to measure two parameters. Okay, but there's one important assumption here is your measurement should be reflecting the truth. All right, this is an assumption that we make for every experiment, for every production line. But is it really true? Have you ever doubted about the precision or accuracy of your measurement systems? Okay, let's say we have, this is not mine, but have a look here. This is good. We have this ruler. Right? We want to measure, say, this dimension. Okay, I make a measurement and I submit the data. I say, okay, this measurement, this data set is in control, for example. But what if this measurement is not accurate? Is that possible? For this one, what are the potential reasons to make this inaccurate? This is a wooden ruler. What are the possible reasons? Expand or shrink because of temperature. What else?
Grading themselves might not.
Yeah, this scaling, grading may not be accurate, right? Anything else? What's that?
If we are not measuring correctly.
Yeah, you may make mistakes when you make measurements, right? I may measure from the very top bottom, or I may measure from a little bit off the bottom, right? All of these errors actually happen in every measurement, is that right? But in this scenario, we normally don't consider that. We take it for granted that our measurements are accurate. And we do our control charts, we do acceptance sampling, we do design, we do everything based on our assumption that our measurement is accurate. But however, you may not be sure that your measurement is actually both accurate and precise. And it's true that not all gauges are reliable. I'll give you one example. I work with Ford on the engine machining process. We use some laser holographic profilometer to measure the surface, high resolution one. And for each surface, it gives us like a million to points to measure the measurements. And just one day, one engineer from the Cleveland factory asked them, so asked the supplier of the measurement system, oh, how can I know this is really reflecting our product? If it shows some variation, what if it is from your own gauge, not our product, right? So then let me be debating. If you have some variation, you don't know which source contributes to this variation. And actually, for that measurement system, we did a measurement system analysis, and we found that measurement system actually was contributing more than half of the variation reflected in the data. So then, if you have some out of control scenarios, you may blame the gauge supplier rather than your own production line. So if that happens, it not only reduces your confidence in your control chart, it's still part of your data, right? But also it reduces engineers' confidence in your decisions. Is that right? So this topic today we are really going to learn about this gauge R&R study. How do we do that for measurement system? Some people also call this measurement system analysis or MSA. So gauge R&R or MSA, they both mean the same thing. the objective is to know whether a measurement system is capable or not. So that's the objective. So how do we do that? Recall that in modern quality monitoring or quality control, this one major goal is to identify variation sources. So according to what we learned in the first half of this class, the total variation can be decomposed into two parts. There are two types of reasons that can contribute to variations. The first one is what? The small variation, the chance process, right? It's inherent, they cannot avoid it, it's always there. Or the second type? Ensemble process or root process. So this process is more destructive. They can render your process to be very incapable. But here, the total variation, I didn't specify this variation is measured or is really there. So what if I say the total measured variation or total observed variation? Then there's a third possible source contributing to this variation, which is measurement errors. Okay? So if we have this decomposition, the goal is really to quantitatively estimate each of them. So for this one, we already know we can use 3 sigma or 4 sigma, whatever you want, right? You have sigma head, you can have R chart, X bar chart to do estimation, you can estimate your natural variation. And for this one, you can also measurement. You can take measurement of a number of products. You take X bar, you take R, you take S square to do our estimation. But for this one, it really has to be estimated, but really we don't know how. So the objectives, there are 3 objectives. First, determine how much of the total variation is due to the gauge or measurement system. To know how much this contributes to the total measured variation. And second, you want to isolate the components of variability in the measurement system. So in the measurement system, even within the measurement system, there could be multiple sources, like operator errors, right? Or the inherent measurement system errors. We also want to know which part contributes the most and how much. And finally, we want to make a decision whether or not the gauge is capable. I give you a 3D profilometer, you want to tell me whether it's capable or not. So that's the 3 goals of gauge and R study. So how do we do that? First, let's take a look at a model. Okay, this is about data modeling. So let's have a model first. Assume we have a manufacturing process producing a number of products every day, okay, over a month. And we collect many products, and we make measurements using a specific measurement system. For each part, we measure multiple times. We repeat this process. So the reason we want to do this is, even though with the same part, same gauge, same operator, you measure multiple times, you may still get different readings. Is that right? Can you give me an example? Anyone is interested in monitoring his or her weight? So you may want to step on a scale and check your weight. Right? Over the day, you have some variation. Even though within the same time period, you measure yourself twice, you may have this reading for some reason. You don't know why. Right? So that is really the variation in repeated measurement. So then we have this model. Okay? Yij is decomposed by 2 parts, xi plus eij. So the subscript here, I is a part number. So we have, let's say we have n parts. So I will get a value from 1 to n. And j is the index for the measurement sequence. So for one product, you measure 10 times, for example. So j will take a value from 1 to 10. Okay? So the Yij is really what your read from your gauge. It's your reading. Okay, so this is your measured numbers. And Xi is the true value of part I. That's why we don't have J subscript, but it's a true value for all the repeated measurements for the same part. Okay? And finally we have an error term. The error term is for part I at J's repeated measurements, we have error term given by Eij. So normally, typically, you assume Eij as 0, right? So we have this relationship y is equal to x. But here, we want to study the contribution of EIJ in your merit value in YIJ. How much portion does EIJ contribute? So that's our goal, right? So we're measuring multiple parts. There's another source variation, which is part-to-part variation. Like you measure this pointer, that pointer, you have two different pointers. So there's another variation, which is part-to-part variation, or product-to-product variation. Alright? So the total variation combination given by this formula is equation sigma total squared is equal to sigma part squared plus sigma gauge squared. So there are only two variation sources. One is from your part-to-part variation, and second is from your gauge. So we want to get estimate for both of them, and also get estimate for sigma total squared. So that's our goal for this study. So we can also simplify this using the measurement data model given by this sigma y squared is sigma I squared plus sigma e squared. So how do we measure? Any thoughts before we go through the methods? Any ideas how can we do this? Okay, let's forget about the modeling part. Let's first, if I ask you to design an experiment to estimate these three parameters, how will you approach the problem? Yeah, some thoughts.
I was thinking like, how would you measure the true value?
Yeah, that's a very good point. This is always unknown. Right? Anyone knows how to define 1 meter? Right, we use that every day, right? 1 meter or 1 millimeter, 1 nanometer. How do we define 1 meter? I think this is 1. Yeah, this is like 1 meter. How do I know if this is 1 meter? Okay, I give you this question. How do I know that if this is 1 meter? You know, meter is the most important unit in a metric system. So how do I know whether this is 1 meter or not? This is a 1 meter ruler. Don't tell me because it's a 1 meter ruler, I have 100 centimeters. No, it's not acceptable. So how do we know if this is 1 meter? So, okay, standard gauge. Where do we get standard gauge? You are using gauge to measure gauge. Right? From manufacturers, how do you know the manufacturers give you the accurate gauge? It's an endless problem, right? But there's one definition for 1 meter. If you check, if you Google it, it's defined as some portion of the the circle of the Earth, the globe. Okay, that's the definition for 1 meter. Okay, but it's not possible for us every time we go to internet and check that, right? So normally xi is unknown. All right. How can we at least get a better idea about xi? How can we do that? If you want to design an experiment to estimate these three parameters, how can you do? Here I have several keywords here. Okay. The first is part I, part 1, 2, 3, 4, meaning I have multiple parts. All right. A second keyword here, I have repeat the measurement. If I repeat the measurement for one part multiple times, can that somehow increase my confidence in my measurement? Yes, right? So you have more measurements. Probably you have a better idea of what you are measuring. And also, there's a hidden parameter here, which is operator effect. So, particularly for those type of measurements, if I measure it or you measure, you may have different readings. So then we have a third contributor, which is operator effect. So how do we do that? So actually, let's go through one example and then let's see how can we do that, right? So this is a table for the measurement data. So assuming that an instrument or device is to be used as a measurement system for some K coordinate heuristic. And the core engineers in this project want to know that they are getting correct readings. So they design this experiment. Here we have 20 units, all right, 20 parts. And there are only one operator, but the one operator measures each part twice. We have 2 readings for each part. So then we have in total like 40 measurement experiments. And then we have construct this table. Okay, so each row is still one calculate X bar and R. Does this look familiar to you somewhere? We have seen it somewhere, right? So I have this reading like X double bar and R bar. So any thoughts about this? Where did we use this? X bar R bar. So in X bar R bar, we use X bar to monitor one type of variability, which is within sample or between sample. What is X bar? Between sample, right? X1 bar, X2 bar, how different they are. That's all we're doing. So this is between sample variability. How about R? R chart. R measures the range of one sample, right? It is within sample variability. Right. So here, what concepts can we borrow from X bar R chart to this example? So for each part, we measure twice. So the R value is not within sample variability, but it's rather within part variability, right? So here we have variability in repeated measurements. All right? How about X bar? X1 bar is the measurement for part 1. X2 is for part 2. So X bar is really reflecting part to part variability. Is that right? So basically between sample, but here I like the between parts. So what we can say, we have part to part. Right? Remember that in X bar R chart, if sigma is unknown, we can estimate sigma hat using R value. Is that right? We have some proportional ratio, is that right? If we can estimate that, we have sigma. So then for here, we have the sigma as sigma process. Similarly, we can do the same thing for this data set. If we estimate sigma, what is this sigma? Is sigma part, sigma repeated environment, or something else? So sigma here is really reflecting this, right? So then it should be the estimation of this. If we have sigma value for this, does this mean that we have an estimate for the gauge repeatability? Alright? Is the logic reasonable to you? If we can estimate sigma process for a regular X bar R chart, the sigma process is really estimation of R value basically. Alright? So similarly, this sigma we estimate from this R value, it will be reflecting the variability in repeated environments, and also will reflect the gauge capability. Okay, so that's the whole idea. But still, for X bar, it doesn't matter. It's the same thing. So here, X bar is between sample is part of variability. So if we have estimation for say X bar, how different X bar is from part to part. So we have a good sense about part to part variability. Alright? Okay, so more formally, we can construct this control chart, X bar and R chart. And this is our formula. Sigma gauge will be R bar divided by D2. So back there, sigma process is R bar divided by D2. Okay? So then we also have a subscript which is sample size. D2 is a function of sample size n. Alright? So here, which sample size should we use? It's not a true sample size. Which sample size should we use for this value? So here, it's not a real sample, but it is still the number of data points in one row. Alright? So here D2 should be equal to 2 sample size. So that is the number of repeated measurements for each part. So the D2 value when n is 2, we have 1.128. And we have this calculation, we have a sigma gauge as 0.887. Does that make sense? Okay, so now let's take a look at this data. R value sometimes is 0, meaning that for part 4, the operator measures twice, get the same reading. But n is very rare, right? Only 5 occurrences. But most of the time, we have something like 1 or 2, meaning that the same operator measures the same part twice. He or she can get an error up to 2. If you divide 2021 by 2, or divide 2 by 2021, it's roughly 10% error, right? What does that tell you? For each measurement, you may have a 10% error. That's huge, right? But if I do this estimation, the sigma hat is only 0.887. Is this number small enough to give you confidence in the gauge? Do you feel confident in this gauge? Do you feel comfortable in using it for your production? If there's a production engineer correction you, okay, it's not nothing is wrong with my production. There's something wrong with your gauge. So how do you argue with the engineer? All right, let's keep that in mind, okay? So now, let's go through each chart. So X bar chart, so this chart, it tells you the distinction power of the instrument, meaning that for different parts, can they be different in your gauge reading, okay? That's X bar chart. And R chart is the magnitude of measurement error or the gauge capability. So with smaller R value, we have a better gauge. Okay, right? So R value is the difference between measurements made on the same unit using the same instrument. Okay, same operator, same unit, same product, same instrument. You can get different readings. So R value is really reflecting that difference. And then R chart, if it is in control, it means that the operator has no difficulty in operating the gauge properly. If you have a very huge R value somewhere in the R chart, it means that for that part, the operator was really confused by some experiment setting. Right? It may use a different baseline, or it may use a different reading technique, or something else, or maybe he's tired or something. But if that happens, it means something's wrong with the measurement process. We want to dig into that root cause and try to eliminate this in the future measurement experiments. Okay, if the R chart is out of control, like I said, the operator has some difficulty in using the instrument. You may want to reduce this, right? Okay, let me ask you. If I have a gauge, have small R value for all of the readings, can I be sure that this gauge is good? No. Why?
You may have offset.
Speak up.
You may have offset.
Yeah, you may be measuring all wrong numbers, but you're very confident. That, right? So there are multiple paths to this problem. Did you say something different?
No, I was just saying, like, maybe even if the R value is small, I mean, the operator would be measuring
The wrong
values.
Yeah, and also it would be X bar would be under control, right? But then the gauge may be good for using. It's very easy to use, but it gives you wrong numbers or inaccurate numbers, right? So that's also possible. So there are really a few dimensions in determining whether a gauge is improvable or not. All right, so now let's review, the formulas for this. If I give you the data set, not in the example, but more formally, let's introduce the measurement on system analysis methods. So the total variance is resulting from two independent variation sources, product and gauge. If they're independent, sigma total square will be equal to sigma product square plus sigma gauge square. We don't have any covariance here, so they're independent. It's reasonable because the product to product or measurement to measurement, these two seem to be independent. So we make this assumption. And then from the actual sample measurement, we know that sigma total square is 0.05. So this number is calculated simply by getting the sample variance. So sigma total square is simply the variance of all of these 40 numbers. That's S squared, sigma total square. And then sigma gauge is estimated by using R bar divided by D2, what we learned from our chart, where we have this value. And by using this formula, we know that sigma product square is a subtraction of sigma total square and sigma gauge square, which is 10 minus 0.887 squared. So be careful with this. This we are estimating sigma gauge, not square. The standard deviation, not the variance. Okay. We can make this calculation. We found that our sigma product square is 9.26. And we can also calculate standard deviation by getting the root of it, is 3.04. What does this result tell you? We have one production line. The same production line produces 20 supposedly to be identical products, 20 products. And we have one operator measure each of them twice. We have 40 readings. And we take this experiment and we estimate that our sigma gauge is 0.887. So this is 0.887, and sigma product is 3.04. Okay, what does this result tell you? Do I have a good gauge? Intuitively, is it good? This point something is a small number, right? And intuitively, it looks not bad, right? So how about the process, the production process? Do we have a good production line? It's good. You don't give me answer because there's no answer. It depends on your upper and lower specification limits and the sigma, 6 sigma, right? But let's compare these two. It seems that the total variance or total variation in your measurement is mainly due to sigma hat product. It's mainly due to part-to-part variability, right? So the gauge gives you a pretty good measurement. So this number compared with this number is pretty small. Is that right? So, okay, what is a perfect gauge? Well, what is a perfect gauge?
Give you the same exact number every time.
Yes. So y equals x, then that's perfect, right? But here, this number is not a 0. If this is not 0, we have a perfect gauge. Perfectly precise gauge, right? And if this is true, then we have a very good gauge. But here, this number is very small compared to this. Meaning that even though we have some errors, but compared to the part-to-part variability, it's not that large. Meaning that we are pretty much adequately estimating the variability in your process. So you may wonder, do we have some easy method other than arguing like this, talking like this? Yes, there are some numbers. The first one is called the PT ratio, precision to tolerance ratio. So PT ratio is defined as 6 times sigma gauge hat divided by the specification limits range. Upper means lower specification limits. If this is less than 10%, we consider this gauge as capable. Okay? And also, you may notice that if you do not have this, you really don't know whether your gauge is capable or not. I'll give you one example. If I want to measure, let's say if I want to measure the board dimension, okay? If my sigma gauge hat, sigma ruler hat is 0.01 meter, in measuring this dimension, do you think it's good? Let's say my upper and lower spectrum limit is like millimeter range or maybe centimeter range. So then this number that's give you another zero. It's very well. Okay. So then let's say my spec limits are I give you the maybe 1.51 meter and 1.52 meter. So this is about 10 centimeters, right? You divide this by 10 centimeters, what do you get? 10 millimeters. So this is 0.1 millimeter, is that right? Divided by 10 millimeter is only 1%. So it's way smaller than 0.1. So now this scale is pretty good. Alright? Let's say we use that ruler. Let's say that ruler is pretty good in this case. But however, if you use this same ruler to measure a nano manufacturing product, we need a nanometer precision. And my spec limits are now, I don't know, maybe 101 nanometer and 102 nanometer. So now what is my PP ratio in this case? So now my PP ratio is sigma gauge x, which is 0.30 from there? Yeah. Okay, so this is meter, right? And this is 1 nanometer. And we know this is 100 nanometer, alright? 0.001 meter is 100 nanometer. Divided by 1 nanometer is 100. It's a terrible gauge, alright? So your sigma hat is so much larger than your product dimension and precision requirement. So in this case, it's no longer capable. It really depends on your application. Okay? Alright, so back to this example in the previous slide. If we have upper and lower spec limits are 60 and 5, then my pitch ratio would be 6 times 0.877 divided by 55, which is 0.097, which is close to 0.1, but it's good. It's smaller than 0.1. So probably have a capable gauge in this case. Alright, so that's one metric for this. Another metric is the ratio of measurement system varies the total variability. So this sigma gauge square divided by sigma total square. So this also gives you a number. And in this example, we have 0.877 squared divided by 10, which is 7.83%. But for this one, we don't have some strict value like 0.1. Okay? We don't have that. But for both of them, the smaller values mean that we have a better gauge. The smaller the better. Okay? And for this one, the requirement can be placed by the production engineer, like how much precision they need in measuring this. It's really application dependent. Okay, so back to the question we just discussed. What makes a good gauge? So what gauge is good? So there are two dimensions at least, alright? The one dimension is gauge accuracy, which is the ability of the instrument to measure the true value correctly on average. That's the case, on average. The gauge accuracy does not consider variation in variability. As long as the average is close to the true value, the gauge has a good accuracy. Right? On the other hand, we have a gauge precision, which is a measure of the inherent variability in the measurement system, which is the variance of the measurement data. So this metric does not consider whether you are measuring the true value or not. It only concerns with whether you are measuring you are getting the same value repeatedly. So here I have this chart, right? The horizontal axis is precision, the vertical axis is accuracy. If we have this example, all the dots, measurement, like blue dots are the measurement, black dot is the real ground truth. If they're close to the center of it, it has both good precision and good accuracy with clustered dots. So all of them are close enough. That give you good precision. And they're close to the center of the true value, they give you good accuracy. And this example, like all of the points are very close to each other. So the process is very repeatable, but it's off the center. It only has good precision, but not good accuracy. And this one instead, this one is the worst case because the center is not there and also they are scared off. So this one, even though it has poor precision, all the dots are very far away from each other, we have pretty good precision because the center, the average is still close to the center. Does that make sense? So in order to have a good gauge, you need to have both as satisfactory. Okay. Here in this figure, this is my target, what I want to measure. If I get my arrows close to the center in average, I have an unbiased estimation and I have a good accuracy. But if they are all clustered very close to each other, even though they are far away from the center, we still have good precision. Okay? In gauge and R study, we primarily focus on gauge precision rather than accuracy. So precision is about all the sigma square, sigma half, sigma. Okay, so that's about precision, and that's a concern of gauge and R study. So in the previous example, we have seen that we can estimate sigma gauge square, sigma half using R bar or something similar like that, right? But in that example, we only have one operator measuring multiple times. So what if we have multiple operators? Do you anticipate the different operators will introduce different variability values? Sure, right? How do I estimate that? So actually, sigma gauge square or sigma measurement error square can be further decomposed into two terms: sigma repeatability square and sigma reproducibility square. So that's what I mean by gauge R and R. So one R and second R. And also we're using R charts. It's not relevant, but there are many R's, right? So the repeatability is defined as inherent precision of a gauge. You can imagine like this: if we use one operator to measure multiple times, we only have sigma repeatability square. On the other hand, if we have multiple operators measuring the same stuff multiple times, then we have reproducibility, which is decided by different operators or conditions. So in order to complete a full gauge and R study, we estimate both. So how do we do that? There are two methods. The first method is based on control charts, X bar and R chart. And second method is based on ANOVA, which is our analysis of variance. So let's go through both methods. The first one, in order to calculate the variability terms, sigma or R or whatever, first we need to design an experiment that gives us multiple measurements. So here's a typical layout for gauge and R study. Let's say we have three parts, okay? And we have two operators. For each part, each operator, we have two measurements. So this is a repeatability. And this part-to-part variance is sigma product square. And furthermore, this operator-to-operator variability is sigma reproducibility square. So we want to estimate all of them. So we have three levels of factors. Level 1 is parts, level 2 is operators, and level 3 is repeats. And in this example, we have three parts, two operators, and two repeats. So we have in total 12 experiments, the product of these three numbers. So how do we construct control charts based on this measurement? So we collect data and store the data in this table. Still, each row is for one part, but we have multiple column blocks. And the first block is operator 1, and second block operator 2, and third block operator 3. Each of them consists of two measurements, 1 and 2, and here and here. And for each of them, we can calculate one X bar and one R. You can consider this as one sample, second sample, and third sample. Okay? So using this, we can further calculate the X1 double bar. The meaning of X1 double bar is the average measurement of operator 1 for all 20 parts. That's what X1 double bar means. R1 bar is the average of all R values for all parts. So that's R1 bar. The same for X2, R2, X3, and R3. So with these results, how can we calculate sigma hat for the three parameters we just mentioned? So now we have 120 experiments, and we have many R values and many X bar values. Let's first try to distinguish what they represent. What does R1 bar mean? R1 bar is average of all R values for all parts. Does this reflect part-to-part variation or operator-to-operator variation? No, definitely no operator. Everything here is operator one. So about part-to-part variation. Does it reflect that at all? No, because it is the average of R. Each R shows the repeatability of one operator. So this, you can consider this as an average repeatability for operator one. Also we have R2 bar and R3 bar. Okay, so with this, now let's do control part. So which term in the table reflects the device variability? X bar, R bar, or X double bar? Which one of them? Like we just discussed, each R value is one repeatability measurement, right? So then we have R1 bar, R2 bar, and R3 bar. Then we have R double bar. Okay, so R double bar is the average of all R values in this table. We take all the R values together, get average, that's R double bar. So R double bar is a good estimate for the device variability, alright? Okay. So then sigma repeatability is given by R double bar divided by D2 sample size of 2. Because we have 2 repeats for each part. So we have sample size of 2. So here in this example, the sigma repeatability is given by 1.02. Okay, so that's for that. So this is total average that we just discussed. And for the second task, which term reflects the variability due to operators? What values can possibly give us operator effects? X bar. So in this table, okay, so I have X1 double bar, X2 double bar, X3 double bar. If I want to know how different, like how much difference can different operator give me, which value should I look at? Should I look at R1 bar, R2 bar? Now we should be looking at, okay, let me ask you this. For the same part, if 3 operators married 3 times, the difference can reflect operator effect. Does that mean? Is that right? So we should really look at this direction. For each part, we have X bar, X bar, and X bar. If they are identical to each other, meaning that operator has no effect at all. Now we look at this direction for the final row. We can look at X1 double bar, and X2 double bar, and X3 double bar. So now by getting an average, we eliminate the effects of part to part and repeats. So then if X1 double bar, X2 double bar, and X3 double bar, they are very different from each other. It means that the operators are getting given the values for same parts. Does that make sense? So that's why we should calculate R X double bar. We just calculate the range for the 3 X double bar values. So in this case, the maximum is 22.6 and minimum is 22.28. So that is my R X double bar. This value and this value. So then I have this. This reflects the difference among 3 operators. Okay, I have this range, and the sigma reproducibility is given by this value divided by D2 sample size of 3, because I have 3 operators. That makes sense? So in this case, my value is 0.19, right? So here is the average for each operator. X1 double bar is only for operator 1. X2 is for operator 2. Even though I have double bar, but that's for operator 1 all measurements for all parts. So the difference between these X double bars are reflecting the difference between operators. And you count how many operators you have, you get a sample size for these values. Alright? Okay. Finally, I have these two ready. I calculate sigma gauge square, which is given by 1.08 in this case. And my PT ratio is 0.11. It's about 11%. So do you think this gauge is capable or not? It's probably a hard call, right? It's close to 0.1, but it's not that good, but it's not that bad. So then, again, that may depend on your requirement, on your measurement precision. But this one, I would say, is not bad in this case. Okay. So now, if I want to compare these two, what does the difference between sigma reproducibility and sigma repeatability tell us? So here, obviously, repeatability sigma is much larger than reproducibility. What does this mean? How should we interpret this result?
The workers measure
Has to be done.
the workers they don't measure uniformly.
They don't measure uniformly. Is it within operator or between operator? So between operator is given by this value. Yeah. So reproducibility is using between operators. Repeatability is the same operator. So it means that the repeatability is worse than reproducibility, meaning the gauge is not easy to use. Okay, it's true for all operators. No matter who you choose to measure the system, you always get a large repeatability standardization. So the reproducibility is small, meaning that it doesn't matter which operator you use to do this task. Okay. Okay, so in summary, here are my formulas. Sigma repeatability hat given by R double bar divided by D2. And the sample size is the number of repeated measurements for each part. Okay? And sigma reproducibility is given by R X double bar divided by D2. You calculate X1 double bar, X2 double bar for all operators. And then you get a range of all of these double bar X values. And the range of this can give us the estimate for reproducibility. It means the difference among operators. There are two scales. One is within operator, and second one is between operator. Okay? So this value gives us the between operator variability. And this sample size should be equal to number of operators. Right? So now we have this ready. And I have the estimate for sigma gauge square. So sigma gauge square or sigma measurement error square is the sum of repeatability and reproducibility. Okay, we have this. And in the bigger picture, we will have sigma total square. Yeah, right? We have 20 parts. We have many measurements. Then we have a global sigma square, which is sample variance. So the sample variance is always larger than sigma gauge square, and the remaining of it is actually sigma product square. So in that example, we can actually estimate sigma product square by subtracting sigma gauge square from sigma total square. So this should be the sample variance. So then you have everything ready. Okay? So here's another example. In the gauge analysis study, we have 3 operators, and we have 5 parts. And for each part, we measure 4 times. Okay. So then we have the table, and we summarize the statistics in this table. We have x1 double bar, x2 double bar, x3 double bar, and r1 bar, and r2 bar, and r3 bar. So how do we estimate sigma repeatability, reproducibility, and sigma gauge? We use the equation for sigma hat is R bar divided by D2. It's plugging in the correct sample size. So in this example, my x R double bar is given by this 1.7, and R x double bar is 1.4. So that is the range of these three values. Okay, so that's that. And my repeated rate is R double bar divided by D2. So sample size is 4 because we measure each part 4 times. So then we have 4 here. And for recursive rate, we have sample size of 3 because we have 3 operators. Okay, so we have all of the estimates. The sigma gauge square should be a sum of these two. Okay, and we have this value. That's the PG ratio. We have 0.118. Again, it's probably marginal control. It's not too good and not too bad. Okay. Okay, so that is everything I have for X bar R chart. There's a second method where we can use ANOVA, analysis of variance. So X bar R chart is very convenient if you do not have a calculator. So ANOVA is more convenient if you have a computer. So ANOVA can be more efficient and more accurate. Okay, let's see how can we do that. So the idea of ANOVA is that you will have a measurement. The measurement variance comes from several sources: part, operator, repeated measurements, and the interaction of part and operator. And by using some linear regression models, we can actually have this model. In this model, mu is the ground truth, the production mean, production average, and P is the effect of parts, O is the effect of operators, PO is the interaction between operator and parts, and finally this is random error. We assume that all of these variables are independent and normal distributed variables, and we can have this relationship. So far we have this model, and next step we're going to estimate all of them. So how to do that? How to estimate the variance components? We start with the full model. Okay, don't get scared by this. It's very easy. Okay, we have this total model. This equation is sum of squares. So this total sum of squares, this part sum square, and this operator, this P and O interactions, and this is errors. And we have the degree of freedom for all of them. And first of all, we have the total number of experiments, which is the product of P, O, and N. So P is the number of parts, O is the number of operators, and N is the number of repeated experiments. That's the total number of degree of freedom we have in this experiment. And then the degree of freedom from part is P minus 1, because we lose 1 degree of freedom because we are estimating the parameter regarding part. Okay? Similarly, we have all of this like this. And the mean square is actually given by the ratio of sum of square and degree of freedom that's calculated for all of them. Alright? And then the expectation of mean squares will be equal to the expectation of mean square will be equal to the sum of squares. Okay? So then we have this ready. The sigma square is the mean square of error term, expectation of it. And for the operator, we have 2 terms, sigma square plus n sigma PO square. Similarly, we have that for all the terms here. And then we can conduct f-test for each variance component. So f-test is normally used for model selection. So mean square P divided by mean square PO is FP. Similarly, we have FO and FPO. And for significant components, P values should be smaller than alpha value. Again, we have alpha value here. Okay? If the P value is smaller than alpha, the corresponding term is considered as significant. And finally, we have these formulas to estimate each term. Does that make sense? Okay. Alright, so that's the full model. I assume that the interaction between an operator and a part is significant. But it may not be that case. If that's the case, we can have a reduced model. We remove the PO part. And then we have 3 terms remaining in the model. So again, we do the same procedure and have this result. Make sense? Okay. The good news is that software, basically every software can give you this in one comment. So here's one example from one data set. Okay, so the full model, our ANOVA method, we have our ANOVA table given like this. So if you look at this column, is the source, a part, operator, interaction, and the repeatability with the measurement error. So this is corresponding to MSE term. So in this, we have degree of freedom part, 19, which is 20 minus 1. We have 20 parts. So DF is 20 minus 1, which is 19. And operator, we have 3 operators. We have 2 as a degree of freedom. Similar, we can do the calculation for all of them. And we calculate sum of squares, mean squares, and F value and P value. There was all the calculation here. So, how do we calculate this number? What is the degree of freedom of part on the interaction term of part and operator? It's 19 multiplied by 2. It's 20 minus 1 times 3 minus 1. Okay? How about this term? The repeatability degree of freedom. Why is it a 60? So that is the total degree of freedom minus all the remaining things. We have this. Right, so 119 minus this, we have 16. Okay. So how do we calculate mean square? Let's go on mean square. So how do we calculate that? And it's also how do we calculate mean square? Have you taken course like a linear model or linear regression? This type of courses? No? Okay, I will give you more formulas after class, right? So F test is just the result of MS1 over MS2. We have an F test statistic, and then you can use you can use hypothesis testing to get p-value. Okay, so that's the idea. So the key observation from here is the interaction term, the p-value is very large, so almost 0.9, meaning that this term is not important at all. So then we can get a reduced model by removing that. We have the same results, but with no interaction term. So this will be our final model. Even though we have still some parameters that are not significant, we still keep them because we want to estimate the contribution of operator. So we keep this. The degree of freedom for these 2 terms will become 1 term because these 2 are combined. So we remove this, so the degree of freedom will be added to the repeatability term, the error term. We have 98 now. So then I have this calculation. Based on mean square and the operator process part to part, we can type the sigma hat square using this formula. Right? We can calculate each term. And we have a negative value for sigma PO square. That's kind of reasonable because we know PO, the operator interaction, is not significant at all. We just set it at 0. Okay? And then we have some of this. I don't know why. So then I have this error term and reproducibility, which is the sum of these 2. So sigma gauge square is actually 1.0669. So the PT ratio will be given by this, 0.11. So still remember what we got using R chart, X bar R chart? It's similar, right? So if I give you one data set, here's 2 methods, it is expected that you have similar results, but not too different. It can be different, but not too different, right? So sigma gauge square is the sum of these two terms, so reproducibility and repeatability. Okay, and sigma gauge hat is this number, and in infinity ratio calculation we're using sigma hat, not sigma square. Okay, this will be sigma, not sigma square. So we have this result. So this is for the full model. We already know that this is not significant. We can run this program again for the restricted model. Okay, so these two we combine to this one, and we have this result given by this slide. So the sigma operator square is these two, subtraction of these two divided by p times n, so which is 0.01, and sigma repeatability is 0.88, and have this result that repeat everything. The PD ratio a little bit smaller, 0.105. So this result will be considered as the final result for this gauge in our study. So again, this value is close to 0.1. It's not a good or bad, it's just marginal capable. Okay? So the reduced model results are given like this. We have this value and this value. So the part-to-part variation is 10 something. And the gauge R&R variance is variability is only 0.89. So compare this to this, what do we land? We already know that the PD ratio is roughly 10%. But if you compare these two, the ratio of these two is very small, right? It's around 1%, even smaller than 1%. It means that if you measure this process over and over again, the process variation will be dominant in your data. You may not even notice that there's something different caused by your gauge, because this is so large. Okay? So that's the conclusion from this model. And I have one more example. So in this example, I have 3 operators. I have 10 parts. Each measurement is repeated 3 times. So then I conduct a factorial experiment. I have 3 levels for inspector and 10 levels for parts, and 3 levels for repeated measurements. If I use ANOVA, I get this result. Okay, and in this slide, the key is to use this column, divide this column by the degree of freedom, and we have F statistic, and then we have F value. So by the way, this is a full model because we have this. But here, the full model shows that the interaction term is very significant. The p-value is almost 0. And it means that we should take this term and do the calculation for the full model scenario. So then we calculate the MS mean square for each term, and we calculate the F statistic. So we have to calculate MS and divide that by the degree of freedom, and we can estimate the sigma hat for the 3 terms that we're interested in. So here is a calculation between SS and MS. So they are all by the degree of freedom. So this is part number, is 10 minus 1, is p minus 1 here. And SS part is the sum of squares. Okay? Regarding how to calculate sum of squares, I assume that you know that, but you don't know, but I will give you some tutorial to do that. Okay? But it's okay if you don't know that, because the software will give you the results right away. But you should be able to know, tell me what does your result mean. Okay? So the sigma hat square is estimated this. It's a subtraction between MSP and MSPO over O times n, the operator and repeated measurement. We have sigma p squared. Okay, we have all the tabulation. We have all the results for sigma p squared, sigma O squared, and sigma hat squared. So here, the various components and this, they are 1-to-1 matched. And in this result, actually, we know that sigma gauge square is 1.8. And the PT ratio in this case would be 0.27, which is much larger than 0.1. So we should claim that this gauge is not capable. Does that make sense? Yes.
But in this one, there is like also the effect of the operator. So how can you just say that it's like there's interaction term, right?
Yes.
So
Operator or repeatable within operator or within operator, all of these are effects from the gauge. Okay. So you don't separate sigma O and sigma PO from this because all of these are counted as a gauge. Let's say if you have a gauge, you marry different operators, you use it, they have different values. It means that your gauge is not properly designed. Alright? It's still considered as gauge error. Does that make sense? Okay. So if you have the interaction term, you keep that in the final calculation. If this term is not significant, this value is larger than 0.05, for example, you remove it and then rerun the program and get a new estimate for the MS SS terms. You recalculate this. Okay. Okay. So this gauge is not capable. That's the conclusion. So in summary, we typically think of sigma square as a repeatability various component, and the gauge reproducibility is the sum of operator and the part operator. So here, sigma reproducibility is the sum of these two. And sigma gauge square the sum of these three, but these two will form one term which is sigma reproducibility square. Okay, so this contains the effects of operator and operator part interaction because it's all about operators. Okay, so that's why we have this reproducibility for that term. So if we have a negative estimate for sigma OP square, for example, in the previous example, if that's the case, we can just set it as 0. Or we can remove it and rerun the model with a restricted model or reduced model. And then we just update our results. But I don't anticipate much difference between two models. But that is 0 is very small and also the p-value is large, right? So these two models will give you very close results.